Good afternoon, and welcome to the Brain and Behavior Research Foundation's Meet the Scientist monthly webinar series. I'm Dr. Peter Tarr. I'm BBRF's Editorial Director for Science and Chief Science Writer, and I'm standing in today for Dr. Jeffrey Borenstein, BBRF's President and CEO, who regrets that he can't be with us due to another obligation. Today, Dr. Chris Sege will present a talk entitled Fulfilling the Promise of Non-Invasive Brain Stimulation as a Precision Medicine Tool. BBRF is the world's largest private funder of mental health research grants supporting transformative discoveries in order to develop improved treatments, cures, and methods of prevention. The high quality of the research we fund is made possible by the BBRF Scientific Council. This is a group of 195 prominent mental health researchers who review each grant application and select the most promising ideas with the greatest potential to lead to breakthroughs. The Scientific Council guides the Foundation to fund creative and impactful basic, translational, and clinical research relevant to the whole spectrum of mental health. One reason that research funded by BBRF has such great impact is because we do not limit our focus to one illness or one condition. Since 1987, the Foundation has awarded $461 million to fund more than 6,500 research grants around the world and across a broad spectrum of brain illnesses, including addiction, ADHD, anxiety, autism, bipolar disorder, borderline personality disorder, depression, eating disorders, OCD, PTSD, schizophrenia, as well as suicide prevention. And so now I am delighted to introduce Dr. Christopher Sege. And Dr. Sege is an assistant professor in the Department of Psychiatry and Brain Sciences at the Medical University of South Carolina. He is a recipient of a 2023 BBRF Young Investigator Grant. Our webinar will begin with Dr. Sege's presentation, which will then be followed by a Q&A. And to submit your questions, which we welcome, please use the Questions tab on the control panel on your screen. Please feel free to submit your questions at any time during the presentation. Following the presentation, I will ask as many questions as possible in the time allotted. And so now I am pleased to introduce Dr. Sege. Dr. Sege?
Thank you so much, Dr. Tarr, for the introduction, and thank you to all of you for attending this webinar and for having interest in this topic. Also, before I start, I want to make sure that I really thank the Brain and Behavior Research Foundation for supporting my research and also for giving me an opportunity to talk about it in this forum. I really think this is a wonderful thing that the BBRF does, and I'm excited to talk to all of you. Oops, my screen is not moving on. Here we go. Before I get into the science, just a couple of notes on disclosures. I do want to let everybody know that I am a part of contracted research between MUSC and Attune Neurosciences, which is a company that also provides the ultrasound device that we use in one of the studies I'm going to talk about today. But outside of that, no other financial interests to disclose. And getting as kind of a segue into the theme of my talk, I want to start by acknowledging the teams that I work with at MUSC that are really conducting the kind of transformative research that I'm going to talk about today. My work is just really a small part of this. So first of all, I'll acknowledge the Sleep and Mood and Anxiety Research and Treatment Division at MUSC, which is really conducting transformative work, seeking to integrate psychological and psychiatric treatments in new and innovative ways, and also disseminate those types of treatments in a broad area within our state of South Carolina. Moving from that, I'll then also acknowledge the Brain Stimulation Laboratory, which is really the home of a lot of the really cutting-edge innovative research that's seeking to transform this already kind of revolutionary mental health field of non-invasive brain stimulation. A lot of the work that's being done in this lab is really driven by the head of the lab, Dr. Mark George, who's actually the individual who conducted the first test of the kind of leading technology within this field, transcranial magnetic stimulation, as a treatment for depression back in 1995. And I'll say that despite that accomplishment, Dr. George also is by no means resting, and he really continues to work tirelessly to continue transforming this field in new and innovative ways. And then within the BSL, a lot of other investigators are conducting a lot of innovative research to follow Dr. George's lead. That includes Dr. McTague and Dr. Kevin Caulfield, who are also both collaborators on the research I'll present here today. And that kind of brings me more into the theme of this talk, which is transforming brain stimulation and fulfilling its promise as what we call a precision medicine tool. What I'm really talking about when I say this is taking brain stimulation away from an approach that's been historically often applied, where this technology has been used to target kind of broad disorder classifications using a standardized or one-size-fits-all type of approach. And instead, us in the BSL and other groups throughout the world are looking to increase the degree to which we can apply this technology in a way that's really with precision to more specific kind of psychological processes and behaviors, and also with individualization, where we're making it work for individual concerns. There's all kinds of different types of work going on within this area. For example, work that's looking at different brain areas as targets to target specific symptoms. Research that's going on to see if we can actually sync the stimulation of, the delivery of brain stimulation up with the occurrence of significant events in the brain in a very precise kind of way. And then also a host of research that's investigating how brain stimulation may be paired with specific types of tasks and exercises in order to use it to target more specific kinds of processes and behaviors that drive symptoms rather than trying to target just the symptoms themselves. And that last area is where my work fits in, where the work that I'm conducting in partnership with the BBRF is looking to see if we can pair brain stimulation with emotional coping types of practice exercises in order to help people as they relearn fear behaviors that are driving clinical levels of anxiety. So before talking about that research, to give kind of an outline of how I'll talk about this, I want to start by talking just a little bit about the clinical context, which is anxiety and related conditions. I'll talk a little bit about kind of our goals with treatment for those conditions, as well as the current approaches that we have and limitations of those approaches. In addressing those limitations, I'll then move on to talk a little bit more in detail about brain stimulation, and I'll focus in particular on two particularly promising technologies, one of those being transcranial magnetic stimulation, and then another newer technology, focused ultrasound. After giving some of those details, I'll then move on to talk about the work that we're doing, which is really trying to use those technologies to target specific fight or flight types of responses that, like I said, really drive clinical anxiety. And finally, to close that out, I'll end by talking just a little bit about how the kind of basic science work that we're doing right now might oh no. I don't know if anybody can respond to me and tell me if they can hear me. I see feedback from my mic, so I'm going to continue. I'm going to close out. Okay.
Yeah, we can hear you.
Perfect. Sorry about that. Thank you. Anyway, I'll close out the talk by talking about kind of the future and how this might lead to the development of new treatments. But before we get to the future of treatments for anxiety, I want to talk just a little bit about the kind of current state of anxiety as a clinical area and our current treatments for treating kind of maladaptive fight or flight or freeze responding in these conditions. In thinking about anxiety as a clinical area, I will say that I, along with many other clinical psychologists and psychiatrists in the US, am really influenced heavily in how I think about these conditions by the American Psychiatric Association's classification system, the Diagnostic and Statistical Manual of Mental Disorders, which really describes a variety of different mental health conditions within a so-called anxiety spectrum of disorders. And it also describes other conditions like obsessive-compulsive disorder and PTSD, which are not within that category of disorders, but are still considered to be heavily related. And so as we look at these different kind of conditions from a clinical symptom perspective, when we see individuals with these conditions come to our clinic, they can present with very different symptoms, But a commonality amongst all these conditions is that these conditions really at their heart are posited to be driven by disruptions in the operation of a kind of basic fight, flight, freeze response system in the brain. And that really functions as kind of a or even the primary driver of symptoms for these individuals. According to influential models of how this kind of works, this kind of disrupted operation is really driven by overly conditioned associations between situations or objects in the environment, and then physiological and brain responses that serve as a kind of inherent alarm signal that automatically tags those situations as dangerous and inherently kind of reduces the perceived available response options down to a few kind of high urgency choices, these being to kind of fight it out, to freeze up, or to just get myself out of here. And given the strength of this signal for individuals with clinical anxiety, this signal comes to over time to drive an over-reliance on avoidance coping as a way of managing these situations and the fear that comes along with it. It's really that kind of cycle of fight, flight, freeze activation with avoidant behavior that really drives the impairment in anxiety and related conditions. And as a result, this is also a core treatment target for really all of the treatments that we currently have for anxiety and related conditions. Some of the most successful of which fall under the umbrella of what are called cognitive behavioral therapies. There's a lot of different kind of flavors of CBT treatments for anxiety, but really they all at their heart revolve around exercises and strategies for really countering avoidance in individuals with anxiety, allowing individuals with anxiety to experience the fight or flight signaling and learn that that is not inherently dangerous, and that these individuals can actually manage these situations without a need to run away from it. And at its heart, these treatment approaches, I think, are at the end of the day pretty intuitive in their approach. And I think for that reason, that might be the biggest reason why they've had a lot of success with people over the many years that they've been implemented. At the same time, while these treatments are effective for many individuals, there are still also important limitations to the effectiveness of these treatments. Perhaps the most kind of glaring of which is that while many people do benefit from these treatments, many others don't find it possible to complete these treatments as prescribed. Others do complete the treatments, but still don't achieve benefit at a level where their lives improve. And then growing research also suggests that others might complete the treatment and benefit from it, but also be at a high risk to relapse after the treatment is completed. And in thinking about what might be driving these limitations, one of the key challenges that we still have to think about with anxiety and related conditions is really the very automatic nature of these fight, flight, freeze responses that we're trying to counteract with treatment. So there's been some studies here and there throughout the years that have more or less directly illustrated this kind of automaticity of fear. Here I'm highlighting a couple of studies that I like that kind of illustrate this, where in one study on the left, individuals with a phobic level of fear of snakes or spiders still show measurable physiological responses to images of those things, even when the image is presented in a way where the person couldn't possibly be aware that it's on the screen. And as another example, in a more recent study, with individuals with panic disorder, these individuals were put into stressful situations and asked to press a button whenever they detected panic-like symptoms, and it was found that that button press actually came well after those panic-like symptoms like heart rate increase and priming of a defensive startle reflex had already started to occur. And these kinds of results really illustrate a key challenge with treating fight, flight, freeze dysfunction. And this was articulated by Arne Ullman in this study, where he said that it really could be the case that a lot of individuals with clinical level of anxiety have this fight or flight signal come on and an intense drive to avoid a situation before they're even really fully aware that they're in that situation. And so that drive to avoid can really become very difficult to fight against in that situation. This is then further illustrated by a growing number of research studies that directly tie ingrained avoidance habits to these limitations that I mentioned of treatment dropout and non-response. And this relationship has been found in things like panic disorder, social anxiety disorder, post-traumatic stress disorder, and most recently in obsessive-compulsive disorder, where it was shown that ingrained avoidant habits at pre-treatment not only predicted less likelihood of remitting with treatment in one study, but in another study, it was also found that ingrained avoidance habits pre-treatment also predicted a greater likelihood to relapse, even for individuals who did initially succeed in responding to treatment. I keep getting bothered by this message, so hopefully you can still hear me. It looks like it. With all of this evidence in line here, it really raises a key question still facing the field of anxiety today, which is, given these kind of still existing limitations on even our best treatment approaches, can we further improve these treatments by coming up with new ways to target fight or flight responding more directly and reduce these more efficiently so people can relearn them more completely? And with that, that brings me to talking about some non-invasive brain stimulation tools, which could really be promising in this endeavor and could allow us to target the underlying brain mechanisms of this type of responding in a way that increases the flexibility in those mechanisms and improves the ability to relearn fear responses. Before starting to talk about specific technologies, I'll just say in general, as an introduction to what I mean about non-invasive brain stimulation, this is really a term, non-invasive brain stimulation, or also neuromodulation, as it's also called, that's applied to a growing variety of technologies that are able to use the ability to transmit electrical or magnetic or mechanical signals through bone and skin and fluid into nervous system tissue in the brain or in the peripheral nervous system. And they're able to do that in such a way where they can interact with activity in the nervous system without the need for any kind of surgery. Like I mentioned, there's a variety of technologies available that can do this general kind of thing. And these technologies have really a wide array of mechanisms of action. But despite that, when we talk about using these technologies in therapeutic applications, really all of these technologies have a common goal of enhancing what's called plasticity in the nervous system. And plasticity really refers to the ability of the nervous system to either form new connections by repeated firing or to remodel itself and its cells in ways that make it easier to form new connections in the future or to fire in more adaptive ways. There's some general mechanisms of plasticity that are highlighted below that I won't get into, but I will say that enhancing plasticity is really important for the simple reason that this is really considered to be the basis of relearning and behavior change in adaptive situations, including in psychological treatment. So with that kind of general thing out of the way, I'll talk about some of the technologies that are used to do this. And I'll start by talking about what I think is kind of the leading technology right now, transcranial magnetic stimulation, or TMS. TMS as a technology uses a superficial small electromagnet, when I say small, often a handheld electromagnet, that can be placed on top of the head and used to generate a very rapid and relatively weak magnetic pulse that can travel through the scalp and the skull into the brain and interact with electrical activity in the brain in the targeted area of the surface level of the brain called the cortex in a way that influences firing in that area. Like I said, TMS can be delivered in these very short kind of pulses of magnetic energy, and then that can be delivered in different ways in order to bring about different effects. We can deliver TMS in a single pulse kind of fashion, where we deliver one pulse, and the effect of that is going to be to cause just an acute burst of neuronal firing in the targeted area of cortex that the coil is placed above. Building on, and that I should say that that single pulse can be used to generate even directly measurable effects at times. For example, if we put the coil over the motor cortex of the brain and deliver a single pulse, we can immediately see the effect of that, for example, in a thumb twitch that might be caused by stimulating that area. Building off of that, we can then also alternatively deliver TMS in a repeated pulse session where we deliver many of these pulses all in a rapid row. This type of session is referred to as repetitive TMS or RTMS. And this type of application can be used to generate more longer lasting types of changes in the propensities of neurons to fire. I say longer lasting, they'll last beyond just a minute, but more maybe on the scale of an hour or so. And so lastly, building off of that even further to get even more durable changes, we can also deliver TMS by stringing these kind of RTMS sessions together in a multi-session course. And that can be used to produce more durable changes in neurons that can support new, more active connections and ability to form new connections. And it's really this last form of application of TMS that's what's leveraged in clinical applications of TMS. Here I'll say that the first standard course of TMS was approved by the FDA in 2008. That was approved for major depressive disorder. And a very standardized course was approved at that time, where TMS was approved to be delivered to a standard neural target called the dorsolateral prefrontal cortex, or DLPFC, and delivered in a very standardized way with a kind of constant repetition rate of TMS pulses over the course of many sessions delivered over the course of many days. And after its initial approval, this kind of standard initial course of TMS as a treatment has been found to be effective for many individuals with major depression, even individuals who haven't responded to a number of other more frontline types of treatment for depression, medication, or behavior therapy. And even despite that effectiveness, there continue to be additional innovations and developments since that initial approval. And a lot of these developments have come around the areas of improving our ability to target TMS specifically to the brain area we want to hit, in kind of using computational processes to model what we think stimulation looks like at the level of the brain, and also developments in our ability to deliver TMS pulses in different kinds of rhythms that sync up more closely to the natural rhythms that occur in the brain in order to achieve a stronger effect. All of these adaptations have led to the kind of most recent step forward in depression TMS, which is the Stanford Accelerated Intelligent Neuromodulation Therapy Protocol for depression, or SAINT TMS. And this was FDA cleared in 2023. And this protocol really leverages the most kind of up-to-date advancements in TMS that we have, including leveraging targeting developments to where now we can target TMS not just to a brain, just one brain region, but really to a specific sub-region of that area that has the strongest connections with other areas in the brain that are relevant to depression. This protocol also leverages other advancements in our ability to deliver TMS in more accelerated fashions. So now, instead of just doing one session of TMS per day, we can really deliver many TMS sessions within a single day and shorten down a course of treatment from 5 weeks down to as little as 5 days. In addition to this exciting step forward in depression TMS, other recent developments have also occurred in terms of moving TMS beyond just a treatment for depression. And so those have come in more recent FDA indications in 2017 for obsessive-compulsive disorder, and then in 2020 for quitting smoking. And these FDA approvals have really been built on further advancements with TMS approaches, where we've really developed new ways of being able to closely pair TMS with behavioral exercises, including situational exposure or exposure to craving-inducing cues. And in addition, there's also been technological advancements with our TMS coils, new coil orientations that allow us to reach a little bit deeper into the cortex to areas that are more relevant to these other disorders outside of depression. And so really, all in all, TMS is really an exciting technology with a lot of advantages in therapeutic application. I'll also say that these indications are now all covered by insurance as second or third line options in the treatment of these conditions. Generally, TMS is approved as a treatment after other more frontline medication or behavioral treatments have been tried and found to be unsuccessful. But like I said, TMS as a treatment option has a lot of considerable advantages. Others of which I'll mention here is that TMS is really very safe and really has a very minimal side effect profile. The one kind of main consideration that's generally brought up is that it is generally the case that TMS is contraindicated for individuals who are at a higher risk for having seizures. I'm going to point out that TMS is a technology, in contrast with other technologies like ECT, it is not the point of this technology in order to induce a seizure. And it's really very unlikely that it would, but for individuals who are at an increased seizure threshold, TMS can have an increased risk of triggering a seizure to occur. Outside of that kind of situation, TMS is really very safe in a wide variety of situations, and like I said, has very minimal side effect profile. At the same time, as a treatment tool and also as a research tool, there are some limitations to TMS that really need to be considered. The biggest of which that I'll point out is that despite advancements in the technology, TMS really has limits to the depth that it can reach within the brain, to where now still to this day, TMS cannot stimulate at brain areas that are located below the most surface level of the brain, which is the cortex. Other areas that are central to psychiatric conditions like the amygdala are situated below the cortex, and these areas cannot be directly stimulated with TMS. Also somewhat related to that consideration, TMS is also somewhat limited in the amount of precision that it can achieve. It is relatively precise, but still achieves this brain stimulation spread on the order of a few centimeters, which in terms of the brain can be quite big, especially when you're talking about targeting some other smaller areas. It may not be possible to use TMS to precisely target just that brain area. With that in mind, that brings me talking about a newer and exciting technology called low intensity focused ultrasound, or LIFU. This technology uses a different form of technology to stimulate the brain. Here, rather than using magnetic transmission, this technology uses a mechanical transmitter that can generate ultrasonic waves that can travel through bone and fluid around the brain into brain tissue to a targeted depth. This technology uses an array of these so-called transducers that produce these ultrasonic waves, and those arrays will be programmed in very specific ways to generate a very precise beam of ultrasound waves that will travel to a programmed depth. And based on this technology, we can use this to really overcome some of the depth and focality limitations of TMS. It really is the case that focused ultrasound can reach just about anywhere in the brain and can do so with a high degree of precision. So unlike with TMS, it may be possible with LIFU to stimulate areas like the amygdala. Like TMS, at the same time, LIFU can also be patterned to produce different types of effects that we may be interested in producing. But here's where I'll say that because it's a newer technology relative to TMS, this is an area of ongoing research where we're still figuring out just exactly what that patterning might look like in order to produce the optimal effects that we're looking to produce. With that being said, like I said, LIFU is a newer technology, came about around 2002. And with that said, there are no clinical indications for it as of yet. But I will say that the preclinical work with this technology is coming pretty fast and furious. And at this point, there have been demonstrated effects of low intensity focused ultrasound on a variety of kind of specific kind of processes and responses, including we've seen effects on basic sensory processing responses in the brain. We've seen modulation of sensory perception, like pain perception. And we've also seen some examples where low intensity focused ultrasound can change the way people are reporting their mood in a specific session. So a lot of exciting research is coming out with LIFU, and going along with some of the effects that we're seeing, that research is also demonstrating that LIFU, like TMS, is very, very safe and can have very minimal side effect profile. So in thinking about moving this towards clinical application, those are very important things to have. And in addition, the main strength of this technology is really its ability to reach anywhere in the brain. At the same time, there's, at least at this point, a limitation of focused ultrasound that needs to be considered, where unlike TMS, where TMS can be applied to the cortex of the brain and really oftentimes be applied in a way where we can immediately elicit a measurable response, focused ultrasound, at least to date, has not been applied in this way where we can directly measure the effects of that stimulation in an immediately observable way. And so at least at this point, it could be that TMS is maybe a better technology right now for stimulating the cortical level of the brain, whereas focused ultrasound opens up doors for potentially stimulating deeper areas. With all that being said, that brings me to the current work that we're doing here, where we're using each of these technologies and investigating whether we can use these to specifically target fight or flight circuitry in the brain. And also, by extension of that, how we might be able to best do this in a way that helps people relearn fight or flight responding and move towards a more adaptive kind of fight or flight approach. In talking about targeting the fight or flight circuit in the brain, I just want to talk in general about what that circuit looks like, and mainly just to say that I want to emphasize that fight or flight circuitry in the brain really is not about one particular brain area or even just a few brain areas in a small part of the brain. Fight or flight circuitry really does involve a widely distributed network of areas in the brain that communicate with each other in order to kind of regulate fight or flight responding. Many of those areas are at the cortical surface of the brain, including an area like the ventromedial prefrontal cortex, which has been demonstrated to have key roles in kind of regulating the degree to which fight or flight activation might come about across different types of contexts. And then beyond that, there's also other areas that are deeper in the brain, including the amygdala, which is really more kind of centrally key to forming some of those more kind of automatic conditioned responses where fight or flight activation is kind of comes to be automatically activated in particular situations. So with all that being said, one question that comes up to us as we're doing this work is where might be the best area to target as we're looking to start to treat the operation of this system. At the same time, in addition to thinking about what area we may want to target, we also have to start thinking about whether it might be the case that we may need to target this circuit in specific contexts in order to produce the best effect. Fight or flight circuitry is not a circuit that just kind of turns off, and it's not an all or nothing type of thing. It's really a complicated type of circuitry that has complex interactions between different areas of the brain that are conducted in order to select the best responses in the face of specific types of threat contexts. Here's an illustration of what that kind of complex interaction might look like. And I won't get into the details of this, but this is just to illustrate that in addition to thinking about what brain areas we may want to stimulate, we also have to start thinking about whether it may also be crucial to stimulate that circuitry in the right context, or in other words, stimulate fight or flight circuitry specifically in contexts where we find that it's not working adaptively for people. With respect to doing that, that brings me to a task that we developed that we think has promise in this kind of application. And this is this threat coping preparation task that we've developed, where this task is used to measure fight or flight responding as it's regulated across different threat contexts with varying levels of control over the threat. So in this kind of laboratory-based task, we are confronting individuals with threatening information, in this case, these highly unpleasant, kind of disgusting or violent pictures. And people see those pictures with a cue that comes before each picture that indicates to the person a level of control that they're going to have over that upcoming picture. So across our different task contexts, in one task context, people see a cue that indicates that they have complete control over the threat that's coming up. So they are instructed that once that cue goes away, they're going to have an opportunity to press a button and completely avoid ever seeing the unpleasant picture. And so that's this kind of complete control avoidance context. In another task context, an escape context, people see a different cue before the picture that indicates that they're not going to have that same level of complete control. And no matter what they do, they are going to immediately see the unpleasant picture after the cue goes away. Still, though, in this context, they do still have some level of control to where they're able to push a button in response to that picture and get it off the screen as quickly as they can. That's in contrast to the third task context here, where people see a different cue indicating to them that they have no control over the upcoming unpleasant picture, and no matter how they respond, that picture is going to stay on for a period of time. This task really allows us to look at how fight-flight responding is regulated across different levels of control. In order to measure that, we take a variety of measures, and one of our most kind of useful measures in this regard is a so-called startle reflex measure, where we get this measure by, while people are doing this task, presenting people with, at the same time, very short but kind of jarring noise bursts that elicit a reflexive blink, which we can then measure in the blink muscle underneath the eye. And this elicitation of this reflex really gives us a direct readout of the activation of a fight or flight system, in as much as the magnitude of this blink reflex increases with increasing stress or threat. And so we see stronger blink reflexes as the stress of a given context increases. And so this task approach has really been something that we've been found to be promising for us in a number of research studies conducted before the research I'll talk about next. For one, we have seen with this approach that we can see measurable differences in fight or flight system activation across our different task contexts in general, such that reflex reactivity increases as control over threat decreases. And then in addition to that, and perhaps more interestingly, we also see a measurable and reproducible impact of individual anxiety level on responding in this task that is context specific. And so what we see is that individuals with increasing levels of anxiety also show increasing levels of startle reactivity, specifically in a task context where they're preparing to escape from upcoming threat. So in other contexts of total avoidance or total uncontrollability, even people with very high levels of anxiety don't show any difference in their fight or flight responding in those contexts. But in the escape preparation condition, individuals with high levels or clinical levels of anxiety show a level of fight or flight responding that's really no different from their responding in a totally uncontrollable situation. And so this is pretty exciting for us and raises the possibility of answering an interesting question to us of whether we can not only just use brain stimulation to reduce fight or flight responding, but whether we can reduce fight or flight responding in a context specific way without just having to kind of shut the whole system down. And so that brings me to the research that we've been conducting in partnership with the Brain Behavior Research Foundation. Okay, still hear me? All right. And these are a couple of research studies where we are using a general design of bringing individuals in to complete our threat coping preparation task and a variety of other measures of general kind of mood state and also fight or flight responding, and then receive a session of brain stimulation that's designed to produce brain changes that last about an hour, and then complete those measures again to see if we can produce any kind of measurable changes. And I'll also say in these general designs, we are bringing in individuals for these studies who have a clinical level of anxiety or related concerns. So these are individuals who are actively seeking treatment for anxiety or something related, or they're currently in treatment for one of those conditions. In our first study, we're really focusing on TMS as a brain stimulation technology. In this study, we've recruited 55 individuals with complete data to date. And in this study, like I mentioned, we're looking at TMS as a brain stimulation technology. And more than that, we're really comparing effects of TMS to two different brain sites. One of those brain sites, the medial prefrontal cortex, is a brain area that I've already alluded to as being more intimately involved in fight or flight circuitry and regulation of that type of responding. And then we have another brain area we're targeting, the supplementary motor area, which still has important motor and motor planning and execution types of roles, but isn't thought to be as intimately involved in threat circuitry per se. And so we're really looking to compare effects of those two different sites. And what we're observing in this study to date is, first of all, reproducing our findings that our fight or flight regulation task is reproducing effects that we've seen before, where anxious individuals are showing fight or flight reactivity in an escape condition. That's really very similar to a condition where they have no control at all. And that's before stimulation. So after stimulation, we're then seeing that when we do stimulation to that more kind of removed area, the supplementary motor area, we're seeing no changes in that pattern of fight or flight regulation across contexts. But then when we look at stimulation to the more medial prefrontal cortex area, we do see changes in fight or flight response regulation. And again, as I alluded to, we're seeing that in really a contextually tuned kind of way. So we're not actually impacting fight or flight responding in avoidance or uncontrollable conditions, but what we're really doing is specifically potentially increasing the ability of fight or flight circuitry to downregulate responding in an escape preparation condition. So a context-specific kind of effect. In addition to that, we're also starting to see some potentially exciting individual differences in this pattern of effects. So with these effects that I've already talked about, what I didn't mention to you is that these effects are actually really specific to individuals who are coming in for anxiety-related concerns, but who are not also reporting a level of depression that's in a very severe range. When we do look at individuals who are also reporting severe levels of depression, we see a different pattern of responding prior to TMS treatment, and this is more consistent with potentially more of a blunting of fight or flight responding across threat contexts. And in addition, in those individuals, we're also seeing a different pattern of response to TMS, where the less depressed individuals are showing that specific response to MPFC stimulation, and specifically in that escape condition. In the more depressed individuals, we're also seeing that effect. But in addition to that, we're also seeing a response for the other brain area, the SMA, in the direction to where this kind of potentially blunted reactivity in the uncontrollable condition is being counteracted by SMA stimulation. So to kind of summarize those findings, what we're starting to see with this study is some potentially promising effects of stimulating the cortex, the medial prefrontal cortex in particular, in terms of producing an increased ability to regulate fight or flight or responding in a way that's adapted to the context at hand. In addition, we're also seeing some potentially exciting indications of individual difference effects. We're going to be able to tune this approach to meet different needs of different individuals based on kind of their measurements previous to stimulation. So these are some exciting effects of stimulating the cortical level of the brain. But what's unanswered by this study is what happens if we stimulate deeper in the brain to an area that's potentially more kind of intimately related to just the activation or deactivation of fight or flight responding, and that is the amygdala. So that brings me to our second study that's using focused ultrasound to address that question. This study follows very much the same kind of protocol as study one. The difference here is we are conducting focused ultrasound stimulation to the amygdala, and rather than comparing two different brain areas, here we're conducting two different sessions where one session involves active stimulation of the amygdala, and at another session, we are not actually delivering any stimulation anywhere into the brain. What happens in the sham situation is the ultrasound transmitter is placed on the head and turned on in the same way as at the active session. So it feels very much the same, but what we're doing is deprogramming the kind of transducers that are within that transmitter so that no focus beam is actually being sent anywhere in the brain. So although people feel it the same, there shouldn't actually be any kind of impact on any kind of stimulation on a particular brain area. We have 15 people in this study to date. I will say that 5 of these are currently ongoing, so I'll present data from 10 so far. And what we're seeing here, first of all, again, is a reproduction of our baseline findings where highly anxious individuals, again, are showing increased reactivity in that escape condition. But unlike the TMS study that I talked about before, what we're not seeing with focused ultrasound is a really marked change in that pattern of responding after stimulation. So there might be potentially some minor looking changes here, but what's really important to emphasize too is that there's no real differences in the responding post-active stimulation as compared to post-sham stimulation. Meanwhile, although we're not seeing effects in that task, what we are seeing is some evidence that active as compared to sham stimulation is having some kind of effect. So first of all, as first kind of evidence of this, I'll say that we have queried 8 individuals to try and guess which session was active and which one was sham. And we found that 6 of those individuals have been able to successfully guess which session was active and which was sham, suggesting that something's cluing these folks in. And following up on that, several subjects have specifically cited mood effects as their kind of clue for which session was active. For example, one participant told us that after active stimulation, it just seemed that things that usually bother me didn't as much. And then according to another subject, it was put more as just after that active stimulation, I just felt a little more kind of tired and deactivated after that session. And so this may be not the most kind of rigorous scientific evidence, but luckily we also have additional measurements in addition to our kind of task-based measurements that could speak more to these kind of general mood states. For example, we are measuring resting physiology before, during, and after stimulation. We are delivering subjective self-reports for people to report on their general negative and positive mood states before and after stimulation. And in addition to all that, we're also conducting additional measurements of reactivity to other kinds of unpleasant stimulation. In particular, we're doing measures of emotion ratings and tolerability ratings of unpleasant odors. And here we're also seeing some evidence that active ultrasound stimulation might be doing something. For example, with our physiological recordings, we're looking in particular at an index that has been related to kind of a general state of relaxation or stress, and that index is heart rate variability. And what we're seeing here is that heart rate variability is decreasing over the course of active stimulation as compared to sham stimulation. And then even more kind of starkly, we're seeing great increases in this heart rate variability metric from pre to post active stimulation as compared to the sham. In addition to that, we're also seeing changes in that responding to that odor testing that I mentioned, to where pleasantness and tolerability of unpleasant odors in particular is increasing for both sessions, but that increase is enhanced following active as compared to sham stimulation. In addition to that, we are also delivering these subjective mood measures, as I mentioned, and we're not seeing any change in reported negative mood states that people are describing, but what we are seeing is a change in positive emotionality, to where that's actually being reduced from pre to post stimulation. With that in mind, I will point out that a number of items on this measure do have kind of a positive, pleasant valence, but also are words like alert or attentive or excited. So they also carry kind of a weight of kind of activation along with them. So it could be that people aren't necessarily feeling worse per se, so much as they're feeling a little bit more deactivated from ultrasound stimulation. With all that said, to summarize this, I'll say that these studies taken together might start to be pointing towards stimulating the cortex as potentially a better strategy for improving the degree to which fight or flight responding can be regulated across specific defensive response contexts. But at the same time, stimulating the amygdala could be a promising way to bring about more general kinds of changes in broad mood states. And this could be very useful as potentially a supplement to things like behavioral therapy, as a way to kind of modulate somebody's mood state before engaging with the sometimes difficult procedures that are involved in that kind of treatment. And so with all that being said, I do want to make sure I leave a little bit of time for questions. I'll just wrap up by kind of summarizing things and saying that over the course of this talk, I hope I've talked a little bit about how non-invasive brain stimulation has really advanced tremendously in terms of its ability to kind of treat in a precision way psychiatric conditions like depression and obsessive-compulsive disorder, conditions that haven't responded to other types of treatments. And in addition to that, we've also made great strides in discovering how we may be able to use this technology to treat specific psychological and behavioral processes, including fight or flight system regulation, in a way that could extend brain stimulation's reach even further. And in thinking about how that particular advancement might relate to developing new treatments in the future, it could be that this kind of behaviorally targeted approach to brain stimulation could be used as a kind of precursor or add-on to other strategies like behavior therapy. For example, we may be able to do fight or flight retraining in conjunction with brain stimulation prior to behavior therapy in order to potentially improve the likelihood that people will get a real benefit out of that treatment. In addition, it could be that these kind of effects could be useful in neurofeedback types of training, which is a separate but related area to brain stimulation, where brain activity or physiological activity is measured and showed to people in real time in a way that can guide behavior changes that promote more kind of neurological or physiological states of well-being. And it's possible that measuring and feeding back specific responses and specific tasks, and also responses to brain stimulation, could be used in much that same kind of guiding way. So with that, sorry I took a little longer than I meant to, but I just want to stop and say thank you to Brain Behavior Research Foundation, to my other funders who've supported this research, to my whole team at MESC and all of our research participants, and to all of you. And I'd love to answer any questions.
Dr. Sege, thank you very much for this really enlightening and fascinating presentation. Very interesting. We have a whole range of questions that have come in from the audience. And because we deferred really to the lay audience, i.e. non-specialists, I think the questions that I will ask you that come from them are the most general and the most basic. And
Sure.
Some of this will involve going back a step or two. Just to establish, how good is the data on just standard TMS on treating anxiety, as opposed to, let's say, depression?
I would say that in my view, the opinions are a little bit mixed on that. I think there's been certain conditions where it has been found to show significant promise, for example, the condition like generalized anxiety disorder, and other conditions, I think, where it's potentially a little bit more variable. And so I guess what I would say is I think we've made great advancements in treating depression with TMS, and also treating anxiety that comes along with depression using TMS. And we can really achieve high response rates in that regard. With regard to anxiety, I would say it's potentially a little bit more variable. Right.
And so is that in part your motivation for trying to use these new techniques or combinations of TMS and the focused, low intensity focused ultrasound? In other words, why move beyond standard TMS is the most basic question.
Right. I would say that's definitely the motivation for this type of research. We've already kind of seen that with the obsessive-compulsive disorder indications, where TMS, I don't think the thinking is that TMS can't just be given alone in kind of like a standard way with no other behavioral interventions and expected to have a great impact. It's really the consideration that TMS has to be delivered with behavioral treatment in that condition in order to have that kind of effect. Here, we're looking to even increase the specificity of that even further, so we could potentially increase the flexibility of this approach and really address a wider array of conditions using that type of approach.
Mm-hmm. And in regard to the idea that you have of perhaps in the future wanting to combine TMS with focused ultrasound, can you explain again the reason for combining them? What advantage would that have specifically?
You know, it's an idea that we and others have just started to kind of talk about more recently. And I think it could be potentially fruitful in terms of thinking about this idea of general kind of states versus specific responses to specific situations, potentially a combination of ultrasound and TMS could kind of optimize both of those variables. I guess another example that I can think of that I would give is you can deliver focused ultrasound to the motor cortex of the brain in a way that doesn't produce a motor response, but it does change the kind of firing propensity of that area to where when you do TMS, you elicit a stronger motor potential by doing the TMS. So you're kind of using the focused ultrasound to enhance the impact of the TMS. I would say it's possibly maybe that general avenue where the combination, there could be kind of a complementary and enhancing effect of one on the other sometime in the future.
I hear you. Thank you. And you know, one sees in the literature the reference to the phrase deep TMS.
Yes.
Is that something you're interested in, or is that related? How is that related to this?
It goes back to what I talked about with OCD and smoking cessation treatments, where there have been these coil orientation developments to where different coil orientations can result in a magnetic field that can reach deeper into the cortex. And that's important for OCD, for smoking cessation, where the kind of critical areas are still in the cortex, but they're a little deeper in. So that's that. But even with that kind of deep TMS, I do think there are still limits. It can reach deeper than traditional TMS, but still not so deep to where it could necessarily stimulate an area like the amygdala. And I'll also say that with deep TMS, it is the case that the deeper you get in the cortex, the less kind of precise you get with your stimulation. Right. And so although you are stimulating deeper in the brain, you're potentially stimulating more areas, which could allow you to maybe, not have the effect that you want.
Right, off-target effects. Also, right. One of the listeners asked specifically about how focused low-intensity focused ultrasound can be. You can literally focus it like a laser beam, or what?
I believe that it's on the order of a few millimeters, which is pretty focused. Now, areas in the brain that are important get even smaller than that, so it still could be awesome if we could get even more focused than that. But it's much more focused on the order of a few millimeters as compared to TMS, which is more like the order of a few centimeters at best.
Right. And my final question is, if you can possibly say, where would you hope to be in a couple of years from now, let's say 5 years from now?
We actually have just started to submit new grant applications in this regard, to where really what I'm hoping to do is move down this road of pairing this kind of basic science research with our kind of more established behavioral treatments for anxiety and related conditions, to where maybe we could do some of this stuff as a precursor to cognitive behavioral therapy, and see if that really improves outcomes in a very real way. Hoping that we can get there in just a few years, so we can start to see not just kind of in-lab kind of effects, but also more kind of real-life impactful effects on how people are responding, after they're done with the treatment.
Well, Dr. Sege, thank you once again for providing all of us with a really enlightening and very informative presentation, and you spoke very clearly. So I want to thank you for that, and I'd like to thank the audience for joining us today. And before we conclude, may I ask you to please consider making a donation to BBRF today. 100% of every dollar, you should know, that is donated goes for research, is invested in our research grants. And we can do this because our operating expenses are covered by separate foundation grants. And this means that when you donate $1 for research, that dollar goes directly to the scientists. And to make a gift, you please visit our website, bbrfoundation.org, or call 800-829-8289. This webinar has been recorded, and if you missed any portion of this presentation or would like to share it, please visit the events and webinars page on the BBRF website. And again, the website is bbrfoundation.org. Please join us again on February 11th at 2 p.m. Eastern Time, when we will hear from Dr. Ami Klin. He is an eminent scholar of the Georgia Research Alliance, a professor and chief of the Division of Autism and Developmental Disabilities at Emory University School of Medicine, and the director of the Marcus Autism Center Children's Healthcare of Atlanta. Dr. Klin will present a talk entitled The Crisis of Access to Early Diagnosis of Autism and Emerging Solutions. Thank you, and as Dr. Bornstein always reminds us, together we can dramatically improve the lives of those living with mental illness and enable more people to live full, happy, and productive lives. Good afternoon.